We are witnessing the dawn of a new era in automotive manufacturing, and the compact, white crossover you see gliding across this snow-covered road is the herald of that change. This isn't just a new Tesla model, this is the physical manifestation of a revolutionary engineering philosophy designed to cut production costs by 50%. Codenamed internally as Project Redwood, and speculated by the public as the Model 2, this vehicle is arguably the most important product Tesla has ever conceived. Its goal is simple yet audacious: to create an electric vehicle platform so efficient to build that it can be sold globally for approximately $25,000, making sustainable transport truly accessible to the masses. This detailed explanation will unpack every known and rumored aspect of this vehicle, focusing not just on its specifications, but on the manufacturing and technological breakthroughs that underpin its existence. The core of this revolution lies not in the car itself, but in the factory that builds it. This new vehicle will be the first to be produced using Tesla's unboxed process. Imagine a traditional car assembly line, where the car is built sequentially, moving down a line, gaining parts and complexity at each station. That conventional process is inherently inefficient, requiring complex choreography and long conveyor belts. The unboxed process turns this on its head. Instead of a single moving line, the car is broken down into major functional modules. These modules are built simultaneously and in parallel, in separate zones of the factory, each zone optimized for its specific task. For example, the floor structure, the entire front half, the rear half, and the interior might all be built in different parts of the gigafactory at the same time. Once each of these massive components is complete, almost fully boxed up, with its own wiring, seating, and sometimes even its own drive components, they all converge at a final assembly point. This is the moment of truth, where the unboxed modules are rapidly combined, or married, to form the complete vehicle in a fraction of the time of a traditional assembly line. This parallelism dramatically reduces the sheer physical size of the assembly line needed, shrinks the factory footprint, and, most importantly, simplifies the logistics and automation. This radical simplification is what allows Tesla to chase production targets of 10,000 units per week, which is necessary to hit the volume required for that $25,000 price tag. The traditional constraints of automotive manufacturing are being shattered by this novel approach, which treats the factory as a high-speed machine in itself, not just a building that houses assembly. The unboxed process works hand in hand with the new next-generation vehicle platform. This is a dedicated architecture, smaller than the one used by the Model 3 and Model Y, and it leverages several advanced technologies simultaneously. First, there's the structural battery pack, which is key to both cost and structural rigidity. Instead of viewing the battery as a heavy component bolted to the car, the battery enclosure itself becomes a critical, load-bearing part of the vehicle chassis. This approach, pioneered with the 4680 battery cell, reduces overall vehicle mass and enhances torsional stiffness, improving safety and handling while eliminating unnecessary body and white material. The 4680 cells, which are larger than previous cells, are also expected to be cheaper to produce and offer better thermal management, which is crucial for performance and longevity, especially in varied climates like the one shown in the image. Furthermore, this new platform heavily relies on gigacasting. Instead of stamping and welding hundreds of individual sheet metal pieces to form the front or rear underbody, Tesla uses massive casting machines, the giga presses, to form these entire sections in a single piece of metal. This drastically reduces the number of parts, eliminating hundreds of robots, countless hours of welding, and the complexity of managing a multitude of suppliers for those small parts. For the next generation vehicle, Tesla is rumored to be aiming for even more comprehensive castings, possibly integrating the side rails and parts of the floor into larger single units, a manufacturing feat that further slashes both cost and weight. The electrical architecture itself is undergoing a major change. Tesla is moving toward a 48-volt low-voltage system. This shift from the conventional 12-volt standard is a massive undertaking, but it offers immense benefits. Higher voltage means lower current is required to deliver the same amount of power. Lower current means smaller, lighter, and cheaper wiring harnesses can be used throughout the vehicle. Given that a modern vehicle's wiring harness can stretch for miles and weigh hundreds of pounds, This transition to a 48-volt system represents a significant opportunity for weight and cost reduction across the entire platform. The vehicle will essentially be built around this minimalist, high-efficiency electrical backbone. Powering this new model are highly efficient drive units. Rumors suggest Tesla is focusing on an even cheaper, more compact drive unit that requires 75% less silicon carbide than current models and potentially uses zero rare earth minerals. Eliminating rare earths, particularly in the permanent magnets of the motors, is a strategic move to reduce material costs, simplify the supply chain, and mitigate risks associated with geopolitical dependencies. Despite being cheaper and more sustainable to produce, these new drive units are expected to maintain, or even exceed, the efficiency of the current generation, driving home the entire vehicle's mission of maximum efficiency per dollar. Let's turn our attention to the vehicle's likely form factor and design, which is hinted at by the image. The vehicle is expected to be a compact crossover, sitting slightly higher than a sedan but smaller than the Model Y. This is a critical commercial choice. The crossover hatchback segment is the largest in the global auto market, particularly in Europe and Asia, where the low-cost Tesla needs to find its highest volume to justify the enormous investment in the new platform and manufacturing process. The design philosophy takes cues from the minimalist, almost monolithic look of the Cybertruck, not in terms of stainless steel, but in terms of sharp lines and surfaces that are optimized for manufacturing simplicity. You'll notice the absence of complex curves and intricate body panel intersections. Simple shapes are easier to stamp, cast, and assemble rapidly. The interior is also expected to be even more minimal than the current Model 3. Everything will be centrally managed through the large touchscreen, and there will be a continued reliance on cameras for parking and safety instead of traditional sensors, reflecting Tesla's vision-only strategy. Storage and utility will be key, as the compact dimensions must still offer enough cargo space and passenger room to serve as a versatile family car or urban runabout. This focus on utility, packaged in an aesthetically modern and simple shell, is what will make it a compelling alternative to traditional compact cars from established automakers. Crucially, this platform is not just intended for the mass-market passenger vehicle, it is also the